in this question, here we've got an unidentified compound, and we've been told that, okay, it contains carbon, hydrogen, and nitrogen. And as you can see, the percentages by mass are included in the question. Now, what I'm going to try and do here is, as it asks me to do, I'm going to try to work out the empirical formula. Now, the first thing I'm going to do is I'm going to add up these percentages. I just want to do a check, see what it adds up to. So if I do that, so if you have a go, see what you get when you worked out. And if you do, you should find that you get 100, right? Sometimes in cases like this, the total might not be 100, but in this case, it was 100. Okay. In order to solve the target of figuring out the empirical formula, we're gonna need to compare the actual amount of substance. Like, so we're looking at, well, when we compare the atoms of the different elements, compared the actual quantity of them compared to each other, we want to look at amount of substance, and we know that one of the ways we can try and do that comparison is by getting the molar quantities, right? In this case, we don't currently have the molar quantities, but okay, how do we get there? Well, the tool that's going to enable me to get there is making an assumption about the sample size. So the assumption I'm going to make is that the sample I have of this unidentified compound, the total is 100 grams. Okay, so that's the assumption I'm going to make. Now, as you've seen from our calculation, the total is 100%, right? So 100 grams means, given these are percentages by mass, it means that we're going to have these percentages instead of going to be masses, right? So therefore, we're going to have carbon 34.78 grams, hydrogen 4.35 grams, and nitrogen 60.87 grams. As I said, we're looking really at amount of substance. What we have now is masses. Masses are quite difficult to compare with each other when it's across elements, because each of the elements has a different relative atomic mass, right? They've got different. So to convert it into a format that we can actually compare the amount of substance across these elements present, we're going to use the equation that mass equals moles times molar mass. So this N for moles and MR for molar mass. And when we rearrange that, because what we have already is the mass, so we have this, and we're trying to work out this, right? So when we rearrange it by dividing both sides of this equation by the molar mass, right? We find that this will cancel, and therefore when we make this the subject now, we get moles equals mass divided by molar mass. That being in grams, this being in grams per mole, right? Okay, so as you can see, to get to the moles, we need to use the molar masses, and in this case it's the molar masses of carbon, hydrogen, and nitrogen. So of course we can get that from the periodic table, though given these elements are quite common, you may actually already know what those molar masses are. So I'm just gonna write a quick tally here. So you can see here we've got carbon, hydrogen, nitrogen, right? and I've actually got it here as well. So, but what I'm going to do is I'm going to tally these out in effectively. I'm going to just put these in a list effectively. Okay, so MR of carbon. And what this does is just helps me to formalize my thinking about it. It's like, okay, well, maybe I know this step, right? I know this step, but let me just formalize my thinking, right? So that's the kind of thought process. Let me formalize my thinking, and then you can see on paper in a quite a granular way how everything has been worked out. Makes it a bit easier to spot mistakes, if any mistakes are made. MR of carbon is 12. MR of hydrogen is 1. MR nitrogen 14. Okay, and these are all as we mentioned, these are all in grams per mole, right? So all of these molar masses are in grams per mole. So at this stage, as you saw from the equation, what we're actually going to do now is divide all of these numbers by the molar masses, right? So 34.78 divided by 12, 4.35 divided by 1, 60.87 divided that by 14. So I would invite you at this stage to have a go, figure out what molar quantities you come up with, and I'm going to keep these to, if where necessary, I'm going to keep the answers to 5 decimal places. Okay, so if you did that, you would have come up with, so for moles of carbon, you'd get 2.89833. For hydrogen, quite clearly you would not really need a calculator. I mean, you're dividing something by 1, so and for nitrogen, you're getting 4.34786. So at this stage, as you can see, we don't actually have a whole number ratio between, like, none of these are whole numbers, right? And we know that for an empirical formula, what we're looking for is the simplest whole number ratio. So there's still more work to do before we can get to our empirical formula, or at least even just the molar quantities that will lead us to the empirical formula. So in order to get at least one of these numbers to be an integer, I'm going to divide all 3 numbers by the smallest number among them. And in this case, it's the moles corresponding, in this case, to the carbon, which is the smallest. So that's the 2.89833. So I'm going to divide all 3 values by that molar quantity. And having done that, I would invite you to have a go, see what you get when you calculate these, right? But if you did do that, in the first case, we are dividing a number by itself, so of course we're going to just get 1. In the case of hydrogen, when you do this calculation, what you should get is 1.50086. And in the case of nitrogen, when you do this calculation, what you notice actually, before I actually go into the answer of this, or at least this particular part, you can see that these two numbers, 4.35 and 4.34786, when you look at them from a lens of to two decimal places, when you round this to two decimal places, of course, you actually find that you've got the same number, right? 4.35. And that obviously has some level of probable implications for the pattern we may expect to observe in the final answer. Now, I'm not going to go into the details of what we would expect, but I think just looking at that, you can kind of get a picture, right? Okay, so for nitrogen, when we do this calculation, what do we get? Well, it's going to be 1.50013, right? At this stage, what you find looking at this, it's quite clear that the 1.5, I mean, it's not a whole number, right? It's not a whole number, and it's not particularly close to a whole number. However, if we now go into a process of scaling up, so what we're doing is we're progressively multiplying this. For example, we'll start at 2, then go up by 2, by 3, by 4, by 5, by 6. We'll start from 2 and go systematically upwards until we hit a whole number, effectively, or at least a whole number, which is a number which is very, very close to a whole number, right? Just based on visual inspection, you can infer what we actually need to multiply this by. But generally speaking, as far as the principle goes, we're looking at, okay, well, if you multiply by 2, what we're going to get. In this case, if we do 2 first of all, which is what we would usually start with, right? So multiplying this by 2, what are we going to get? We're going to get 2 here, right? We're going to get 3.00172 here, and here we're going to get 3.00026, right? Okay, so what can we see quite clearly here at this point? Because now we're so close to a whole number that it is appropriate for us to strongly consider rounding to get to a whole number. And if we look at both of the values that we have, if we round them to 2 decimal places, and we're talking about the relative molar quantity associated with hydrogen and that associated with nitrogen. You can see in both cases, when we round it to 2 decimal places, we effectively have 3. Okay, so we're going to round those. Having rounded them, okay, well, in both cases we've got 3. So our new molar ratio here between them is going to be 2 to 3 to 3, right? Now the question arises, is this our simplest whole number ratio, right? Because that is what we're looking for in the case of an empirical formula. Well, yes, it is our simplest whole number ratio. If we do divide this by something that would, I mean, if we divide it by 2, we're not going to get, well, of course, we just had to multiply it by 2. But if we did divide it by 2, we're not going to get a whole number. Nor would we if we divided everything by 3, for example. So we can, based on this, we can say, well, actually at this stage, the formula for the empirical formula with regards to carbon, it would be C2, right? With regards to hydrogen, it would be H3. With regards to nitrogen, it would be N3, right? And we're putting all of that together, that gives us C2H3 N3. Oftentimes, in a case like this, we regard this as an empirical formula, right? But if we were to say, okay, granted, what we've worked out is an empirical formula, but which is what we were trying to work out. We've basically answered the question. But if we were to ask ourselves, well, if this was the molecular formula for something, what might it be? And so what I'm gonna just take a look at briefly is a formula, a molecule which has that formula, right? C2H3N3, right? So if we look over here, what we have is actually the formula for so as you can see, C2H3N3. This is effectively what we worked out in terms of empirical formula. But as a molecule, this molecule has that formula, right? C2H3N3. So we've got hydrogens. We've got one. There would be one here, right? This is skeletal, so don't show it. But there'll be 1, 2, 3. So 3 hydrogens, nitrogens, 1, 2, 3. And as you show, carbons, we've got a carbon here and a carbon here. So that's 1, 2, 3 triazole. Now this is actually a precursor for a medical, like a drug basically, called tazobactam. It's used for other things, but one of the things it's quite known for is being a precursor for a tazobactam. And tazobactam is effectively something which is, you could say it's regarded as something comparable to a bodyguard for a particular antibiotic. So in this case, the antibiotic is called piperacillin, right? And so piperacillin has some vulnerabilities, and effectively tazobactam helps to I'll use the word inhibit. It works to inhibit some of the molecules which would which would otherwise cause the piperacillin to degrade, and sometimes that can lead to it not actually being around long enough to actually do its job inside the body, right, as an antibiotic. So yeah, anyway, long story short, that particular empirical formula, if we look at it from a perspective of it being a molecular formula, it actually serves as a precursor for another substance which serves as something of a bodyguard for another drug, an antibiotic. And yeah, so tazobactam, this is the actual formula here, and piperacillin is here. This is, well, it's piperacillin doesn't have the whole facial expression, but the actual, if you just look, this actual molecule here would be what it looks like. Anyway, yes. So okay, yeah. So that's, as I said, this is the empirical formula.